Hi everyone. I recently did a repair video on YouTube regarding this high voltage power supply. Since I'm starting this super troubleshooter series, now would be a really good time to start talking about high voltage safety, especially if you want to start working on anything with vacuum tubes in it. I'm also going to talk about keeping the device under test safe and keeping your test equipment safe as well. Now, a lot of people don't want to work on vacuum tube gear because it does have high voltage all over it. About 99% of vacuum tube gear has high voltage all over it, with the exception of some space charge tube units, which are basically the older car radios. And, some people that want to design things with tubes that will run at a really low voltage. So again, about 99% of the stuff with vacuum tubes in it has pretty high voltage all over it. And this thing has high voltage everywhere inside it. Now, whenever you're working on something like this, if you are comfortable working on something like this, it's important to make sure that all the capacitors are discharged before you go into this thing and start working on it. Now, there are a couple of tricks that catch some people. So the first thing that I want to mention here is, if in any way, shape, or form you are uncomfortable with working on vacuum tube gear because of high voltage, don't work on it. You need to be sure of yourself before you go probing around in something like this, and you definitely need to have a good sense of your extremities. You want to know where your hands are or hand is at all times. You don't ever want to come across anything high voltage because, the first time could be the last time. So you got to be very, very safe. Again, if you're uncomfortable with working with vacuum tube gear or anything with high voltage in it, just do not do it. If you are going to work on something that has high voltage in it, you need to take all the safety precautions, and we'll mention a few very key safety precautions here today. So this particular power supply has a bunch of different power supplies in it. It has a vacuum tube power supply and it has a bunch of solid state power supplies. Now, the vacuum tube power supply inside this has a tube with an indirectly heated it's an indirectly heated tube. Let's just call it that, all right? It has a filament inside of a cathode sleeve, and it takes about 10 to 20 seconds for the thing to come into emission. So some of the capacitors in here will take longer to charge up. Other capacitors in here that are on the solid state supplies will charge immediately when you click the switch on. Charged, boom, just like that. Now, the thing that's tricky with vacuum tubes is, and a lot of people get comfortable with this and they shouldn't, is once the tubes warm up, they come into emission and they're drawing current. Well, when you click the power off, it takes a while for the cathodes to cool down. So they comfortably drain the caps off for you. Now, the thing is, you can never rely on that. Never, ever rely on that. You always want to go in there and make sure all the capacitors are drained, and that includes these ones as well. So not only the electrolytics, but even these yellow ones. You want to make sure everything is drained off, because a capacitor bank like this can store a lethal charge. So what I'm going to do here is, I have this attached to my isolation supply right now, and in some previous videos here on Patreon, we put together a capacitor discharge unit just for this purpose. Now, you'll see that normally I have a piece of heat shrink tubing on here just to expose the ends. I'm going to show you a technique that makes sure, well, it's a little bit of extra added protection to make sure that you're making contact. And it's a sawing motion. So anyways, I'll turn on this thing just quickly like this. It's on, and now it's off. Just that fast. So the vacuum tube power supply, the one with the 6X4, which is the tube that's right under here, of course the tube didn't have really any time to warm up. So the capacitors that surround this are most likely not going to have a charge on it, but everything around the areas with all the capacitors that are attached to the diodes will, because there is no filaments, right? It's just as soon as you click the switch, they're charged up. So what I'm going to do here is I'm going to go across these capacitors over here first. All right, so it doesn't matter which way the leads are hooked up, because this will discharge in both directions, and one LED will indicate in one direction and one will the other. So it doesn't matter if you have the red lead on the negative side and the black lead on the positive side. It's just designed to discharge. So I'm going to go in here like so. You can see that red LED lit up. And I'll go across to the other side. Keep an eye on these LEDs here. I'll go across to the other side. You see that one lit up as well right by my finger here. Now, these ones here, I'll go across these. Nothing there. Nothing there. Now, this is a screen supply over here. This is a screen supply that runs to this, to the 6L6s here. So you can see there's a resistor that runs to the screen of this tube and a resistor that runs to the screen of this tube here. Now, this is a completely isolated supply. There is really nothing to drain this off. The tubes didn't heat up. So these capacitors technically stay charged for weeks, month, depending on how good the capacitor is. So that's a combination of these two capacitors here. So I'm going to go across this one right here. Put this right here and right here. Now keep an eye on the LEDs on the box. See that? Go across this one here. Never rely on any resistors or anything to discharge anything. I'll go across this cap here. And I'll go across the yellow ones as well, just to make sure. Can never be too safe. Always take the extra time. Again, you can never be too safe. So now the thing is with these capacitors is there's a thing called dielectric absorption, and a lot of people don't think about this. Dielectric absorption is basically, well, in short, without getting into a dielectric absorption explanation, in short, the capacitors appear to be charging back up on their own. So after a while, the capacitors that you have discharged may get up to a charge that might zap you, and you always want to make sure of that. Now, you want to make sure that you discharge these things and they stay discharged. Now, a lot of people feel comfortable by putting shorting bars across capacitors, especially large electrolytics, and it's not a bad idea, but the only problem is that if you forget to ever take one of those shorting bars off before you power the unit up again, you're going to destroy the unit. You're going to blow all the diodes out of it, take the fuse out, and all sorts of things like that. Again, these things here are envious of becoming jumpers, and any kind of a short or, anything, low impedance or low resistance connection is going to make them become jumpers. So you want to be very sure about that. So if you're going to use the shorting bar technique, you have to really make sure that you've removed those things, double, triple check, almost have a checklist beside you. Very, very important. Now, another thing that gets a lot of techs, and that will get a lot of techs zapped, is they think that taking their discharging device and attaching one probe to the chassis and going around and touching all the capacitor leads is going to make sure that all the capacitors are discharged. Very, very false. In this unit here, on the front, there's supposed to be basically a bridge bar that connects the chassis to the negative in this entire system here. So really, the chassis right now is completely isolated. There is no bridge bar or anything, and that can fool a lot of people. And depending on the situation and the piece of test gear, a lot of chassis will sit isolated from the circuitry, so always keep that in mind. Never think that you can use the chassis and run across to all the capacitors. Always go across the capacitors with a discharge device. You never want to rely on the chassis to do that. I'll give you an example again. I'll hit the power supply here and turn it back off. All right, so everything's going to be charged up, at least in the diode supplies here. So again, the discharge device, keep an eye on the LEDs here. So I'm going to go here right to the positive of the stack. So the 600 volts right here, right? Watch the LEDs. Look, nothing's happening. Right to the chassis, see that? Now look what happens when I go across the capacitors. See that? I'll go across this one here. Look at that. See, so you can never rely on the chassis, and it'll be the same thing for this over here, right? This here, go to this side of the cap, nothing. Go to this side of the cap, nothing. But if I go directly across the capacitor, watch the LEDs. See that? That would hold a nasty charge, a really nasty charge in this capacitor right here, because that's just fully charged and sitting that way because it's attached to the grid of a vacuum tube, so there's really nothing to drain it off, right? Especially when the tube is cold, right? There's definitely no current being drawn there at all. So these are all things that you need to keep in mind. And of course, you don't want to go across all of the smaller capacitors as well, just to be safe. Don't take any chances. Now, if you're working on a device like this, it's always good to have an isolation transformer. That's a little bit of added protection. Isolation transformers isolate the device from the line completely. So protection on another level, you really want to make sure that when you're working on devices like this, that isolation transformers are, definitely in your thoughts. Some electronic devices, you need an isolation transformers. If you like working on older radios, older vacuum tube radios like All-American 5s or All-American 6s, I don't know why they call them All-American 6s, because a lot of those radios, or All-Canadian 6s, I've got so many radios that say made in Canada, made in Canada, made in Canada. So there was a lot of radio manufacturing back in those days that came out of Canada, but they're classified as All-American 5s and All-American 6s, so we'll keep calling them that. At any rate, what happens with those radios is they have one side of the chassis directly connected to the line cord. Like the chassis itself has got a connection right to what you plug into the wall. Back in the days before safety was a real paramount thing, right? Now, those radios usually had all Bakelite knobs or plastic knobs. It was in a plastic case so that you really couldn't come in contact with the line. But they had metal screws that protruded on the bottom side of the chassis. And back in those days, they just expected you to take care. That was just the thing. Nowadays, that is not up to electrical code at all. And, everything has to be isolated, no metal exposed screws or anything like that. So the chassis is hot in those older units, and they need to have an isolation transformer. Now, technically, in a unit like this, the transformers themselves act as isolation from the line, right? Because there's no connection. There is absolutely, the chassis in this thing is actually floating. So unless you have that bridge bar on the front there is no connection to the internal circuitry at all. It really is a floating chassis at that point. Now, unless something was shorting in the actual unit itself or shorting in a transformer, again, chassis floats. So whenever you're working on a unit that has a transformer type supply inside of it, so you have a transformer that feeds AC to the filaments on the tubes, or feeds direct current and all that kind of stuff to a vacuum tube rectifier and out, the transformer in itself really is doing the same job as an isolation transformer. But it never hurts to have that extra added protection behind it as well. Say there's a leak in the power transformer from the line to the chassis, so there's even a short in the transformer. Maybe some of the capacitors that are across the line to the chassis are leaky, which in pretty much every old radio they are. Look at they buried them in the transformer of that little oscilloscope. Right? You just wouldn't think there are any capacitors. You would think that the actual transformer had leakage inside of it if you didn't know any better. But they buried some paper capacitors inside the transformer under tar, right? So things to keep in mind. Even some older Hallicrafters units, their power transformers, they had capacitors hiding inside them under the cap. So you had to actually take the cap off the transformer to find them. A lot easier than a depotting, a depotting situation, but still, it needs to be addressed, right? There's things to keep in mind. So with a unit like this, you always want to make sure that you go across each cap. Now you'll see me when I'm going across a capacitor in a unit like this, I'm doing this with the probes. I'm using a sawing motion. Now the reason that I do that is to ensure that I have a really good connection. If there's any type of debris on the leads, if you're going across terminals like this, and you just touch them, a lot of the times there'll be flux residue or something under there that will stop the connection. This is a pretty shiny, polished surface on these probes, right? So you want to make sure that you're moving the probes around like this to make sure that you get that good connection. That's just one extra added step of safety. Now, you want to make sure that when you're doing this, everything is under control. You might even want to insulate up to about this point here if you're just going to use the end to saw with. Because if you do saw and you come across something like that, or, if you're doing something like that, if there are any capacitors that are charged or anything like that, you're going to get a big flash and there's going to be some problems. Now, this is a doubler stack here, right? So if I came across both of these diodes by slipping like that, right, there still is a diode here and the capacitors are charged. So in this situation, nothing would really happen. But if you were to slip and say there was, a connection to the chassis and you slipped and hit the chassis or something like that, yeah, you would, probably take the end of the probe off and receive a big flash. So you got to be careful with that, because when you do short something like this to a chassis and capacitors are charged, when that big flash happens, there's, metal sputtered all over the place. And, if you're above it, you got to be careful with your eyes, right? Because that flash can affect your eyes big time, because you're going to, get metal basically flashing off of everything. Now, when you're dealing with larger capacitors like this one right here, right, this 470 mics at 450 volts, if you ever short across a terminal like this with a capacitor, you will blow these leads right off the capacitor, and you probably even take the tip right off your probe. It'll end right there. So something to keep in mind. Some of the larger power supplies that I've worked on in the past, they have banks of 450 volt, 10,000 microfarad capacitors, banks of them. And they have bus bars this thick as, basically 3 of my fingers running through an entire unit with these capacitors attached to them. If you ever came across that with, say, a probe, a wrench, something big like a hammer, it would blow the hammer apart. It would vaporize the end of a hammer. It's that big. So there's absolutely, when you're dealing with large capacitors, you cannot take any chances whatsoever. Now, even with small capacitors in a power supply like this, it can hold a lethal charge. Those capacitors that I just mentioned, it is a lethal charge. That is. There's just no if, whys, or buts about it. If you come across a power supply like that, it's the end. You got to be very, very careful in high voltage power supplies. This is lethal. Now, here's the thing with people. Some people can take a nasty electric shock and come back. It just depends on how you've come across that shock. And some people, it'll hit them once and they're done. So you never want to take the chance. Ever take that chance. You want to be as safe as possible. You always want to make sure that all those capacitors are discharged, everything, even including these little ones here, even including the little ones, receiving a zap off them. I mentioned in the video, I got a zap off of this one. It didn't feel very good. That was a smaller capacitor. It's just, you don't want to take any chances whatsoever. And I cannot stress that enough. I cannot stress it enough. So I've had my fair share of shocks, and I'll admit it, like one of them put a hole in my hand. There's a hole right here, and that was near fatal. This one right here. And I still don't know where the exit happened. I still can't find out to this day. When this thing happened here, there's a really hard cartilage ball under here. I don't know if you can really see that. There's a big hole here, and then there's a really hard cartilage ball under there. And anyway, when that happened, after, the aftermath, I could not find where I created a circuit. I still to this day don't know how I created that circuit. I came across something and it got me but good. I destroyed a really nice toolbox by flying, and tools went all over the place, and was a really bad situation. So you don't want to take any chances whatsoever. Believe me, I'm not proud of that, and it's a war wound that I wish that never happened. And I've been doing this for so incredibly long that I've had my fair share. And of course, way back when I wasn't as safe as I was now, I was a little bit more careless. So I want you to learn from this, and I don't want you to take any chances. I don't want you to receive a shock, not a single shock, if you are unsure of working on this kind of stuff. And if what I'm telling you scares you, do not work on vacuum tube equipment. Do not work on anything with high voltage. You got to be extremely careful. One shock could be the last. So please, please take note. So this is the high voltage version here that we have just talked about. Now, when the vacuum tubes are on, when I turn that power supply on that I just did, and if I let this sit on for a period of time, all the vacuum tubes will come into emission, and they will drain a lot of these capacitors off on their own. And a lot of techs get comfortable over time and rely on that just to happen every single time. And I've seen this time and time again on YouTube, where guitar amp guys are working on things and they just immediately get in there with the soldering iron and they're moving things around. And I'm just going, man, like, it looks like they didn't check anything. Maybe it was a cut shot or something. They cut a shot out of the video where they went through and discharged it, but it just looks like, boom, they're just jumping right in there. Getting too comfortable. You can never get too comfortable. Even if the vacuum tubes are coming into emission, and they are into emission for a long period of time, you shut it off and the tubes are cooling down, you still want to go through and check those caps. Definitely do not take any chances whatsoever. Any piece of gear that has high voltage in it, you want to test them. Now, there were some vacuum tubes that were created to run on low voltage, and they're called space charge tubes. And they are about the 1% of the units that run on low voltage. They were basically created in the transition area from vacuum tube, high voltage vacuum tube automobile radios to completely solid state low voltage automobile radios. Again, they're called space charge tubes. You can look that up if you're interested in them. They'll run on plate voltages of 12 volts. And they're used in amplifiers, and they can be used in all sorts of things. And a lot of people are kind of jumping onto the space charge scene. They want to make space charge radios, and they want to make space charge receivers just to see how far they can, listen. They have, contests and stuff like that for listening to broadcast band DX, so distant stations. And people are into that kind of stuff, so they want to make low voltage stuff. And that's about the 1% of low voltage, vacuum tube devices out there. There really aren't any low voltage vacuum tube devices that work correctly other than space charge devices. I see a lot of vacuum tube audio amplifiers that are running, the tubes at, 12 volts, 24 volts, things like that on the plate. Yes, I won't even get into that. So that is a mixture of trying to maybe be politically correct and releasing a vacuum tube device to the general public nowadays. Whereas, functionality and safety are kind of a political thing in that situation. So again, I don't want to get into that kind of stuff. That's getting into politics, but really the only vacuum tubes that do work correctly on low voltage are space charge tubes. So something to keep in mind there. Now, what I'm going to do is I'm going to get a switch mode power supply, and I'm going to show you guys what happened to this thing that basically made it not serviceable. So another tech was in there before I got my hands on it. This seems to be the story of what happens to me. So what happens is things go to other techs, local techs, and they fool around with things and completely destroy the device. And then the owner of the device says, oh, maybe I should get somebody a little bit more experienced to work on this. And then, the stuff ends up on my bench, and it has for a long period of time. Now, in the previous video, I mentioned, one of the previous videos actually it was the Macintosh video, I mentioned now that I question anybody that, wants me to repair anything. And, of course, I'm very picky on what I take, and of course, my other business and everything, right? So there's a whole big thing in there. But I used to have ham operators. They would bring things over that were just destroyed by 5 other techs before it got onto my bench. Well, you saw that one that I took on a long, long time ago, that FT1000 video. That was a mess. And the amount of time that I put into that FT1000 video was astronomical. Just to make a YouTube video and to show all you guys, to basically show you insides of an FT1000 and what other techs do, that was 3 weeks of solid video work. And there was so much stuff done off camera as well, that the amount of time that went into putting that video together for YouTube was absolutely astronomical. And now when people say, okay, this thing has been to other techs and they've worked on it, what I do is I'll say, okay, you know what? I'll take a look at it. And a lot of the times I'll look inside and I'll just, go, it's yours. I'm not touching this thing, just because of the amount of time. I would like to make a YouTube video on all of these kinds of things. But when people bring those devices over, the troubleshooting time on camera and everything can make a YouTube video that maybe is 45 minutes long on YouTube last me off camera 3, maybe 4 weeks of work. You don't realize how much work actually goes into it, because it's, it's all stitched together and really fast, and there's no, there's no delay time in a video, right? But off camera work is, 3 weeks of solid work trying to make that come back. The only reason, I'm telling you this right now, the only reason I did that FT1000 is because it was for a very good friend of mine, and he was upset, and he wasn't living local at the time when all of that kind of stuff happened, and I guess he had brought this to somebody else, and that was the issue. So he moved close to me at that time, and then it ended up on my bench. So very good guy, and the fellow that brought it over, very good guy. I don't know if he wants to be mentioned, and I won't mention him here, but yeah, a good friend for a long period of time. At any rate, so there's a little bit of behind the story stuff. So whenever I take on anything, and if you're going to try and repair things too, I strongly suggest that you take a look inside too before other people have been inside the device, because if you're going to start working on people's stuff, or if you're going to start repairing or troubleshooting things, if other people have been inside it, their mistake adds to what you're looking for. If there was an original mistake and they've shorted something out, congratulations, now you're dealing with 2 or 3 mistakes depending on how bad the short was. If it was brought to another tech and he slipped with his probe, now you're dealing with 4 or 5 mistakes. And it just keeps adding. So the actual repair time and the complexity of the repair gets really, really deep, because you're not only dealing with just a common failure point, you're dealing with actual man-made failure points on top of it as well. So it really, really adds to troubleshooting time. So a lot of large businesses, they will say, has anybody else been inside it? And instantly they'll turn down the repair. If it's a virgin failure, they'll take it. Just like I mentioned in that video, virgin failures, no problems. If it's not a virgin failure point, then, unless the customer is prepared to deal with that and pay you for your time, I strongly suggest passing up. Just stuff I've learned throughout time. So what I'll do is I'll grab that switch mode power supply and we'll take a look inside. Quite some time back, this CNC power supply came to me from a company that owns quite a few CNC machines with FRSE drives in them. This is an SEPW type power supply. So this fits into that drive unit. Now, they had brought this to one of their local techs to get serviced, and one of the local techs had destroyed this thing and basically made it not cost effective to repair. There's just so many things wrong with the supply because of one very simple mistake that tech had made. So this is why I now ask people, has this been to somebody else to get serviced? And if it is, and I find other problems that are not related to the virgin failure point, of course, it's obviously going to cost them a lot more money because it's just troubleshooting and service time, right? So what I'll do is I'll just zoom on in here, move this over a little bit. Pardon the shaky camera as I'm zooming in. So you'll see right down here, there's 3 little slots, and that's where a TO220 package transistor fits in. Not this transistor, this is just one I have on the bench, but this one here fit right into there just like so. Now, because the previous tech really didn't know the failure point of this, he's just probing around and looking for things that he really doesn't understand, and he came across the standby supply. He's down here, and he did that, and that blew the legs right off the transistor and destroyed the little transformer that sits here, which is a standby supply transformer, and of course that's absolutely no longer available. So I would have to design another little small board with a different switch mode power supply on it to basically make this thing operate. This thing here has a standby supply in it, so the standby supply is always operating in this thing. And, of course, over time, when the capacitors leak and things like that, this little guy right here goes away, and this guy here, and all these caps, they all go away. Real troublemaker right here. They just destroy things. Well, unfortunately, what was added to it is the bonus of the slip across here. So not only was there a virgin failure point, all the capacitors, but now there's a man-made failure point by probe slipping. And there's a very easy way to omit this. This happens a lot in the industry because these things will go to a busy center, phones are ringing, people are talking, blah, blah, blah. You're working on something like this, bring, and you jump and you short something out, or somebody taps you on the shoulder. And, this is just stuff that happens all the time. So if you're sitting at a workstation somewhere and you're working on stuff like this, it's very, very important to make sure that, if somebody does touch you or, talks to you, you don't slip with your probe, make a big flash, destroy parts and all that stuff. So this is a high voltage supply in here. This power supply runs off of 200 volts AC. And, of course, this is running at the rectified DC on this side here. So it's running at a fair amount of voltage and quite a bit of current as well. You can still see some of the darkness on the traces here. I cleaned the area up really well. Still some darkness on the traces here. So the standard transistor for this thing, a replacement, would be like a BUL 416T or something like that, high voltage NPN transistor. At any rate, transformer destroyed, windings blown off it and everything like that. So this would need a separate little power supply to sit in here to act as a standby supply. And then, of course, once that's working, I bridged in other power supplies here right into these leads. That's the reason there's flying leads on the top here. And on the bottom, I even have the polarity marked, right here. You see that? Two little supplies here. And I bridged those out, and the thing still wouldn't run. So there's other problems that other tech has caused. So there's actually 3 failure points or more in this power supply. The original bridge rectifier was blown. This here is a replacement SCR in the soft start. The caps were replaced. I replaced the caps not thinking that there was going to be this much, this many issues. This was really an extreme condition. So when I phoned or talked to the owner about this thing, he says, we have lots of spares. Just keep the thing as parts. Just don't worry about it. And it just ended up in a parts bin. And this is going to be more of a challenge just to get running because there's so many man-made problems in here. So, again, there was more, lots of failure points. This was gone. Main rectifier was gone. Soft start was gone. Power supply, the standby. This was transistor was blown up. And then when this was all bridged in, nothing started up still. So probably some of the ICs are shot as well. So who really knows how many problems there are? At least 3 plus, issues. And this has been a long time since I've looked at this. This is... this has been in a parts bin forever, so it's all coming back to me now as I'm looking at all of this. So, quite a few failure points in this thing. But anyways, a lot of it could have just been fixed by a piece of shrink tubing or something like that. So when you look at the probes like this, a piece of shrink tubing that'll run right up to the tip. So just the very tip is exposed on a standard lead like this would have prevented all this. Just the tip, because you can see that even if you come across this, if just the tip's exposed, you can see you're not even shorting this right now. Even if you ram this thing right into the center like so, if just the tip's exposed, you're not joining pins, right? So there's a lot of things that can be done, and that's very important when you're working on sensitive circuitry like this, especially around high voltage stuff like this. Shorting this thing out, on a small transformer. It's about the same size as this driver transformer here, right? The driver transformer for the transistors over here, same kind of size, just the windings are obliviated. They're just annihilated from, shorting this thing across here. So unfortunately, this thing, got resigned as a parts unit. There is a lot of good parts in this thing. If another one was to come in that was, say, completely destroyed, there's a lot of good transformers in here, switch mode stuff. I'll just back the camera out a little bit here. Lots of good parts in here, lots of transistors and things like that for another power supply. But unfortunately, just a lot of damage. Now, there's a lot of wires that carry over to the other side. Who knows what's happened on this side? Has the guy been running his probe along there like that? Maybe he didn't discharge the capacitors. Maybe he left these things charged and started probing around and snap. These things here will stay charged for an extremely long time. These things can get shipped, and when they come, these things have a full charge on them. No kidding. They're these old Nishikon capacitors. You would think old capacitors, no good. Let me tell you, those things hold a charge. I don't know, through an entire shipment process and being packed in a box and all that kind of stuff. Just about ready to start on the bench. So these definitely need to be safely discharged. And of course, that discharging device that I showed you that we've put together in previous videos, or here on Patreon in that previous video, is really good for discharging these large bulk capacitors. And again, these hold quite a wallop. Those things are attached right to the line here, right? And this goes to a 200 volt supply. So designed to be on 200 volts, not 220, not 210, 200. So another thing to keep in mind if you're ever working on solid state devices, this thing here, again, solid state power supply, still dealing with high voltage. Stuff's everywhere in modern power supplies. Computer power supplies, same thing. They all have these large capacitors, and they all hold a charge in the power supply. Depending on the power supply you're working on, they could have banks of these things. I've worked on power supplies that have got a whole cluster of these things in one section, just depending on the current demand on the other side, right? So this stuff is available unless you're considering just working on low voltage electronics. This kind of stuff is encountered all over the place. So already we've seen 2 areas that have high voltage: vacuum tube power supply and now a solid state power supply. So you can see it's really everywhere. Working with high voltage is everywhere. Another commonly misunderstood thing is the oscilloscope probe and its connection. For example, this is a story that I've heard time and time again. The story goes like this. They say, I tried to look at the purity of the sine wave in my wall outlet, and when I plugged this into the wall outlet, I saw a big blue flash, and now my oscilloscope doesn't work anymore. Well, this is the reason why. If you have an oscilloscope that plugs into the wall, this barrel connector here, so this is a BNC connector, the barrel of the BNC connector on your oscilloscope is directly connected to the safety ground on your oscilloscope, or the earth lead if you want to call it that. In your breaker panel, in most cases, the earth and the neutral wire are tied at that point. So you have a 50-50 chance. If you plug this thing into the wall, you could see a really bright blue flash. It'll blow this lead off. A lot of the time it wrecks the oscilloscope too. Always keep that in mind. It's never safe. Even though this is a piece of test gear, it's never safe to probe the AC line, because technically one side of the AC line is tied to this. Never forget that. A lot of the older oscilloscopes only have a 2-wire connection, so the case of the oscilloscope is electrically isolated. So you can get away with plugging this in like this or like this, but there's another dangerous thing there. This is attached to the case of the oscilloscope, and a lot of the older oscilloscopes have a metal case. So if you plug this into the hot side of a wall outlet, the entire case of the oscilloscope is hot, sitting on your bench right there. Not safe at all. So never safe to plug anything like this into the wall, no matter what type of an oscilloscope you have. So never forget that. There are battery-powered oscilloscopes that are completely plastic and completely isolated and are specially made for doing this kind of stuff. Rule of thumb is if your oscilloscope plugs into the wall, chances are this lead is directly attached to the safety ground. And never forget, many cases, that safety ground is attached to the neutral in the breaker panel. So technically this is tied to the neutral side. There's a path to it. So you don't want to destroy any very expensive probes. You definitely don't want to take a chance in getting electrocuted or anything like that. So it's never a safe thing to do. So definitely do not try to probe the AC line. Here's an example of a capacitor that's been sitting charged up for weeks underneath a glass cup. The glass cup there to keep me safe from brushing across this thing or forgetting about it. Any guesses as to what the charge remaining will be? Let's find out. Place your bets. All right, I think it'll be safe if I come in like so. Here we go. 419 volts. Still on that. So there you go. There's an example of a capacitor sitting alone that's been charged up. These are great capacitors. Lots of these things I have. So as you can see, they work very well and they hold a charge for a very long time. Let's discharge this thing. Reach over here and grab my discharger. Here we go. Probably can even draw an arc with this. Let's see if we can. Look at that. There we go. Now for something that might be completely unexpected. Dielectric absorption. Let's see what's happening. Look at that. Charging back up. As you can see, this could reach a scary amount of charge in a very short period of time. That's climbing up fast. So, as you can see, this is why a lot of techs, after they discharge these things, put a shorting bar across them. But again, you can't forget, because if you do and you plug the thing in or turn the power back on, you're going to damage the power supply or just destroy it, right? So, something to keep in mind, dielectric absorption is not your friend, in this case, at any rate. So, I hope you enjoyed. If you have any additional safety tips, please feel free to post them below in the comment section. Very shortly, in the next couple of days, I'm going to post another video here, probably in the next few days. I'm going to get the whole video together and parts list and everything like that. I purchased a whole bunch of LEDs for some future projects, and I want to share those LEDs with you and power them up and show you their colors. One of them that I've got for some of the future projects is a really nice blue color, and I've been looking for this LED for a long period of time. It is like a sky blue or a turquoise blue. Very, very nice looking LED, and it's nice and bright. So that should look really nice on some white colored project boxes, because the actual color of the LED case itself is a white diffused color. So it'll blend right into a white project box, and then as soon as the power is applied and the bar graph's going or something like that, it'll glow that nice sky blue color. Should look really, really good. So I'm going to share that with you guys here in the next few days. I'll get a parts list together. I'll share the parts with you and everything, so that way you guys can purchase some of these things if you like. I've got a bunch of different colors and a bunch of different styles and designs. Marie is still working on the artwork for the project boxes, so that is for the project box for the sift and for the leakage tester as well. So I'm going to get those boxes painted, and I'll get the artwork on them, and then I'll share the artwork with you guys as well. So if you guys want to make a carbon copy of these projects, you can do so. So you can make the exact same thing. It'd be really neat to see if you guys can get it exactly the same way that I've put them together. Now, there are a bunch of very nice builds in the community section. So there's a lot of people that have spent a lot of time putting these projects together. So definitely check those out. They're probably down the list now because, it's been a while since the sift has been built, but very soon I will have a completed sift project with some really neat looking LEDs. So that's coming up very, very shortly. So if you're enjoying the videos and you appreciate this safety video, you can let me know in the comments below and hit the heart symbol. That lets me know that you've enjoyed the video. See you guys very soon. Bye for now.